As you can see by the time marker, this is a very long lecture. It covers a lot of different territory, covers a lot of different items and applications. So I would suggest that maybe you view it in sections. You'll certainly get tired of listening to it all at once, but it's also divided up into various parts. You'll be able to identify those by title slides. So take your time, look at them, revisit them even in the future. If you can save these videos or get with me in the future if you want to review one of these topics even after you've left this class, I'm happy to do that. This week we're going to be talking about logic. We'll be looking at logic ladders, programmable logic controllers. Sometimes these control systems are called logic controls or process controls because we're typically trying to control some sort of a process. In any of these logic systems that we're going to take a look at, you're going to see that there's three main parts to that. One is going to be the input section, and that next is the logic or the decision making or the processing. Sometimes this is called a CPU for central processing unit. And also we're going to have the outputs. So the functions of these devices kind of go like this. The input section is gathering information about the real world. These may be coming from switches, they may be coming from operator settings, it may be coming from transducers that are monitoring different levels of flow or light or heat or viscosity, any of those physical parameters that we might want to keep an eye on. In the decision-making area, this processing of the inputs, I'm looking at those inputs and I'm making a decision what to do. And I have designed and constructed the circuitry, whether it's hardwired or if it's software based. In any case, I've designed and constructed this part to provide a specific output based on the states of the inputs. So if I'm trying to control a process, I want to look at that process, see if it's where it needs to be, where I desire it to be, and if not, I will make corrections with my output stage. Let's take a very simple process. The process here that we're looking at is the illumination of an area, say the bedroom. And the process variable that I'm trying to control is light. It's measured in lumens. And the range of our control is going to be from 0% light to 100% light. So in this process control system, as simple as it may be, we still have an input device, an output device. But what about the decision making? What about the logic? What actually makes up the logic? Well, in this very simple system, it's just the wiring. The wiring is the circuitry that we have designed and constructed to perform the operation that's desired. We're providing an output based on the input, and the way that we've designed the circuitry provides the logic that if this is on, then this is on. If this is off, then this is off. So yes, this is pretty simple. Let's look at something maybe a little more elaborate. In this example of a riding lawn mower, we'll say, I've got the process that I want to control, and that's this motor operating or running, and the variable is motion of this motor. We measure that motion in RPM. The acceptable range again is 0 to 100%. So in this particular system, this process control system, I have two inputs, and to make this work, now I have to have input A and input B to be true or high or on, whatever dichotomous terms we use for this particular logic. But A and B have to both be on before I get the desired output. Now this logic that I've desired A and B, an AND function, I'm able to design and construct circuitry that allows that logical function to occur. Now, if we were to look at that on a logic ladder, it would look something like this. You see that I've got to have switch A, which was the key, switch B, which was the switch under the seat. Both of these have to be made before that starter motor would run. If I looked at the same logic with digital logic, it would look like this. This is an AND gate. With an AND gate, all inputs have to be true or high or on in order to get the output to go high or on. So switch A and switch B would both have to be on before the starter motor output would be output here. If I looked at the same thing on a programmable logic controller, it would probably look something like this. We would see the I for an input and another input. So this is the first input. This is the second. We start the numbering with 0. So this is the second one, and this is the output. Both of these have to be passing current before the output is energized. Inside of this, by the way, in these other examples, we have basically run wires or made connections to provide the logical function that we wanted. Inside of here, it's the similar thing because I've got solid state devices like transistors that are doing what we want to do through the circuitry. If I have the appropriate inputs, that's going to provide the output per design of this logic. Let's take another example that's maybe a little more complicated. Here I have a garage door opener. And on this one, I have an input here. This is the limit switch down. This is limit switches are switches where they change states. Their contacts change states going between close and open. If they are struck or moved by physical contact. There are some called proximity sensors that serve the same function of detecting a position, but those can work off of induction or capacitance that you don't actually have to touch it to energize it, to make it change states. You just have to be near it. But in this case, I've got limit switches that actually have to be moved by physical contact. So I have one that whenever the door is down, it touches that limit switch and it opens it up. And when the door comes off of that limit switch, the limit switch closes. That means that that's a normally closed switch. And I have another one when the door goes all the way up. It's closed until the door reaches it, and when the door touches it, that opens the contacts in that switch. But I only have one input to make it go up and down. So my push button does both functions. So how does that work? Well, what I'm shown here is the door is in the down position, which means this limit switch here, LSD, because the door is up against it, it is open as a set of contacts. So if I push the button, the only thing I'm trying to do by pushing that button is get the door to go up. So let's see what happens. I have a 120 volt supply. I've got none of these contacts are closed, so nothing's happening yet. But as soon as I push this button, current can come from the source. It can flow through the switch. It can't go this way because this is open up. It can go this way because everything's closed, allowing current to get to this, and that causes the motor to run in one direction. Now, there's another circuit here where the motor actually is, and when this contact or this output energizes, that causes the circuit to run the motor in one way. And if this output is energized, it activates circuitry to cause the motor to go the other way. So we won't get into the complexity of that. At this point, we just want to see that my control circuit operates like this. Now, once it goes all the way up, it's just going to keep running. The motor's going to keep running up until it hits this limit switch. That's going to cause this to open. And once it opens, this is going to be de-energized and the motor will quit trying to run. All right, so let's take a look at a couple things here. First of all, I don't want to hold this push button down the whole time the door is moving up or down. So the way I can do that is use a seal-in circuit or a latching circuit. And in this case, as soon as I push the switch, that's going to energize this output. This is going to be a relay coil, and we'll look at relays here in just a minute. So whenever this output energizes, it also causes this set of contacts to close. For as long as this is energized, now these contacts are closed, which allows current to flow around my switch and supply itself. And now I can let go of the switch, and I still have an established circuit here. Until this limit switch opens up and causes to drop out, which is going to cause this to open back up again, and then all of this is without power. And the same thing happens if I'm going down. If I want to go down, I've got a seal-in circuit for down as well, so I don't have to hold the push button the entire time. It can go around. Let's take a look at these two contacts. These are called interlocks, electrical interlocks, and the purpose of these is to prevent the motor from trying to run in two directions at once. And just like this coil causes these contacts to close, it also causes these contacts to open because these are drawn as normally closed. That means when this is energized, the contacts change state and become open, which is going to block any current that ever could come this way for it to go down while the door is going up. And the same thing would happen if I'm trying to go down. This picks up to prevent any current from trying to make the motor run two different directions at the same time. So once the motor is up, then you have this situation where this opens up, disabling this coil. And when I hit the button the second time, the only option that it has is to go down. Now remember, this closed right after the door started to go up. It closed and was ready for the next push button to make it go the other way. But even though when we were trying to make it go up and this sealed in, that would have applied power this direction and caused this to try to go down while it was going up. That's why we had to have these electrical interlocks to prevent that from happening. So when we talk about relays, I say this is a relay coil. These are the contacts. Let's take a closer look at relays. Here we're looking at various types of relays, different sizes. This little ice cube type of relay, this is common in a lot of automotive circuits. Here's a plug-in relay that also has a timing function, so we'll take a look at that as well, and various other types that you may have seen in different applications. Taking a closer look at a relay, we see that here's the coil that we were talking about that was represented by the circle in the schematics, and here are the contacts. The coil and the contacts are both contained in the same unit, but the circuits for each, the coil and the contacts, are separate. And in this case, I have a coil that you can see right here, and it's represented this with the schematic. And we know that if you run current through a conductor, it creates a magnetic field, and particularly if it's wound around a core of metal. So we've created an electromagnet here by energizing this coil. And when I do, the magnetic field will pull the steel bar down towards it because it's pivoted back here. It pulls it down, and when that happens, I've got contacts, like switch contacts, that come together. So if I had power, we'll say I had power coming from a power source here, and I had a wire coming from here going to my load, the load is off until these close together by closing a switch that allows that current to flow through the contacts. In this particular case, we see that this is a double throw. I actually can run current this way, or I can run current this way. Now, when this is de-energized, when there's no current going through this coil circuit, this is in a normally closed position here. It's in a normal position when it's de-energized. This is normally closed contacts. These are normally open contacts. But whenever I energize a relay, the contact states change. So upon energization, any power that was being delivered here is now diverted over to this one instead. Here we see one of those plug-in types that we talked about for a lot of automotive applications, and typically these are how this is the socket. This is typically how those pins are labeled, these pins here. And we can see the schematic for this, that 86 to 85 is where I apply power, current for my coil circuit, and over here are my contacts, normally closed and normally open. In an application, it might look something like this, and you can see the operation. Note that when it's energized, the magnetic field pulls this down, and when I de-energize, there's actually a spring back here to let this thing be pulled back up away from the contacts. You can see the contacts here. It's normally closed on this side, normally open on this side. So in an application, let's take a look at this. CR1 is the coil circuit, control relay coil. That's the schematic symbol for the coil. Right now, the level in this tank, this is a float switch, the level in this tank is at a level that we'll just say is suitable. And because of the position of the switch, the float, and the switch that's operated by the float, this is de-energized. And because it's de-energized, the normally closed contacts are connected to the common terminal, shown as terminal A here. Again, this is all part of that assembly, and this actually is in this assembly too. You see the coil and the contacts. So in the normally closed position, power, current coming from a power source is delivered this way and comes out of the relay to this light, a green light that says level's okay. But if the rising level in that tank becomes excessive, this comes up and will close, and this will energize CR1. It will put current through this coil, creating the magnetic field, and this will change states and go up to here. Now the current from the power source is delivered through these terminals out to create an alarm or a red light, or call for maintenance to come and check it out, or some sort of indicator. Here's another example of maybe how it looks in the real world. This is a level switch, and the way this works, actually there's a magnet in here, and when the float, the level of the fluid causes this thing to move up, because this is buoyant, Whenever that comes up, the magnet will cause this contacts to close in this. So this is operated by level, but through a magnetic connection. So in this particular case, it's similar to what I had before, but in this particular example, I've got two different motors. And the one thing I wanted to point out here was I have two different circuits. I have a 120 volt control circuit that's here. That's part of so the coil is energized, operates out of 120, but my contacts, my power circuit is operated off 480 volts. So effectively, I can control 480 volt circuits with a 120 volt control circuit. And if this were a push button, for example, instead of a float switch, then I could turn on and off 480 volt motors or larger with only having to fool with 120 volts at my fingertips. So obviously this is safer. I can create isolation between myself and the power circuit if I need to. So in this case, my 120 volt circuit's operating this control part, and if this were to go up, I'm going to switch from my normal volume pump into a high pump, a high motor pump. So this is what it would look like in a real world. This is what it would look like in a schematic, the control circuit and the power circuit. Here's another example of an AND switch. This is showing how this coil will energize its contacts on other rungs in ladder logic. These individual lines are called rungs. So in this case, this is an AND function because LS1, the mechanical limit switch, and PS4, this pressure switch, both have to be made, both have to be true or high or 1. Like I say, any of those dichotomous terms that's used in different logic systems, but both of them have to be made before this is energized or becomes true. And we see that the effect of this coil on its contacts is a change of states. This normally open contact will close, and it's delivering power now to some other point in the circuit, or even another circuit on other schematic sheets. And the normally closed contact will open, which will disconnect power to this other circuit. Here we see that this coil, when it's energized, has a role in other coil circuits throughout the schematic or throughout the system. So whenever this limit switch here, and it's saying that it's on a hydraulic cylinder, whenever that cylinder is extended, it's coming up against this limit switch, and that motion is causing this to close, and RB picks up. When RB picks up, that's going to close RB contacts here, and if RC is already closed, RF will pick up. Or if RC is not closed, but then closes, then RF picks up. RB also plays a role here, and for it to have any effect on RG, then the appropriate states have to be in place for these sets of contacts. In this case, RD has to be energized, and RE coil would have to be de-energized for that to happen. So here we have 3 input AND situation, a 3 input AND logic situation being performed by this ladder rung. Here RB plays a role, and before the cylinder is extended, this is not made up, and in that case then this is passing current because this is the normally closed contact. When that cylinder extends and this picks up, this will drop out, causing this to be de-energized unless RE has it sealed in. In that case, RE is going around this, so any change in state of either one of these has no effect on RH. We're looking at AND functions. We've talked about the AND already, and here I see this one, and this one. All three of these sets of contacts have to be made up before RW makes up. And once RW makes up, then this set closes. So whatever RX was, RY, RZ, those were other coils in other places in the circuit. But whenever each of these relays pick up, this set of contact closes. When all three of them, and that has to be all three of them, are made, this will make, closing this. Here is an OR function, and if Rx is made, RW picks up and closes this set of contacts. If RY is made, RZ, RX, or RY, or RZ, three input OR logic circuit. All right, let's take an example here and see how we can work through this. This particular process involves spraying different size items, 4 different colors based on 4 different statuses of the device. Let's just say that they are boxes, some sort of a small box. It has to be painted. Now, the 4 combinations is that it can be short and heavy, or it can be tall and heavy, or it can be short and light, or it can be tall and light. Each one of these combinations get painted a different color, and they get diverted into different bins. So as the items placed on the conveyor, it travels down the conveyor for processing. At the end of the processing, the final part of the process actually, is that it will be diverted. These little gates swing out. They're solenoid activated. They swing out, and as it goes down, if one of these is slanted out, then that piece is going to follow it and fall into a certain bin. So each color will get its own bin. And each color represents one of these 4 possible combinations. Now, notice that I have different zones here. A testing zone, a painting zone, and a diverting zone. So as the piece is placed on the conveyor, it is tested. It's tested for what? It's tested for weight to see if it's light or heavy, and it's tested for height to see if it's short or tall. Once it's tested, it leaves the testing zone and it enters through the painting zone. And in the painting zone, it's sprayed the appropriate colors. One of these 4 colors, depending on what color's been designated for what classification of part. Once it's painted, it leaves that painting zone and enters the diverting zone where, based on the color and its classification, it's diverted into its appropriate bin. That's the process. Now, what is the logic that makes that happen? It's this. In this particular case, we're using relay logic, and this circuitry does all the necessary steps to make that process happen, to control that process. So let's take a look at some of those aspects. LS1. Where's LS1? Right here. Okay. And yes, it's labeled entering the paint zone. So yes, as this item comes down the conveyor, it hits this limit switch and it tells the control system that I am entering the paint zone. So when I do that, when this is picked up, now RPZ coil energizes. RPZ, relay paint zone. Now, I've got a seal-in circuit here. Why? Why do I have this? This tells me I'm going into the paint zone. It causes this to pick up saying, yep, paint zone. Why do I need a seal-in circuit for that? Because once this thing travels down and hits that switch, yep, that says I'm in the paint zone. But as soon as it's past that limit switch, even though it's still in the paint zone, the switch is going back to where it was before this thing hit it. So this is actually a type of memory. This seal-in or this latching circuit causes this to remember where this thing is in the paint zone or in this whole process without the switch playing a role in that anymore. And we see that as long as RDZ is not made up, that seal-in will work. RDZ means the part's in the diverter zone, which is down here, and it's not. It's not, so that's not going to be picked up. It means that's going to be closed. So current can flow around this limit switch, keeping RPZ energized. Now, once it's in that painting zone and it gets painted and it goes into the diverting zone and LS2 picks up, that's going to pick up RDZ and that's going to make this drop out because it's not in the paint zone anymore, and that'll happen. And this will pick up and it seals in too. What breaks its seal is if it's in the clear zone, which are any of these four. This is an OR situation. LS3 or LS4. This means that it has fallen to the bin. It's kind of shown here. This diverter swings out this way, and as this comes down, it's going to hit that diverter and it's going to fall off the conveyor into the bin. And on its way to the bin, it's going to hit that limit switch, LS4, and that means the part's cleared because it fell off the conveyor into a bin. And that'll break the seal that says that I'm not in the diverter zone anymore. Now let's take a look at this section here. This section up here has pretty much just been telling us where is that part. It's telling this whole control system, this is the whole control logic or the control system, process control system. This part up here is pretty much telling me where is that part in the process. This part down here now is what's classifying. This is part that's classifying that part. Because if I go through this weight detector, well, let's look at the height detector first. If I go through the height detector, and this is saying, am I in the clear? No, I'm not in the clear. So this allows current to come. If I am tall, then this will pick up and cause this coil to pick up, and it'll seal around the height detector so that when it passes it, it still remembers that that piece was tall when it was in the testing zone. So we come through here, this makes up because it's high enough to trigger this and seals in, it remembers that it's tall. If at the same time the weight detector detects that it's heavy enough, the same thing happens here. It picks up our heavy and seals it in. So if this picks up and this picks up, it remembers that it was tall and heavy. Now, if it wasn't tall, in other words, if this didn't pick up, if it wasn't tall and it wasn't heavy, then guess what? It's short and light, and this picks up. If it wasn't tall, but it was heavy, well, it was short and heavy. If it was tall, but it wasn't heavy, it was tall and light. And if it was tall and it was heavy, it was tall and heavy. So these were made up by these, and by using logic, we were able to identify all the four possible situations, and there they are. And those, in turn, if I'm in the paint zone, and only if I'm in the paint zone, and it's short and light, then it gets sprayed blue. This is a solenoid, And it's up here so that I have pressurized paint. If that's energized, the paint will be pushed out from the pressure in the nozzle and onto the part. So if I am in the paint zone and only in the paint zone, because if I'm not in a paint zone, I don't want any of these to be energized, right? I don't want paint spraying when I'm not in there. So these only work when I'm in the paint zone as identified up in here. So here are the 4 different combinations of color. And also, this is going to, if I'm in the diverter zone, and only when I'm in the diverter zone, these same combinations are going to actuate the appropriate solenoids so that they get diverted into the appropriate bin. And once it's cleared, then I'm going to forget if it was tall or heavy or short or tall. I'm going to forget that. This is all going to clear out. These will both clear out, and it'll be ready for processing the next part as it goes into the system for this control. And so you actually have more than one process in this system. You've got a process that's doing weight detection, one that's doing height detection, one that's doing spray, and another one that's doing diverting into the appropriate bins. And you also actually have a process of going down the conveyor, but that's not indicated here. It's pretty much just turn it on and off. But you could automate that too if you wanted to. This is showing the exact same logic, same functions, but with solid state devices, logic gates. We won't go into that for this, but we'll just put it up there for an example. Now we talk a little bit about signal converters, especially when we're using solid state logic or PLCs. And the reason for that is a lot of the power in the real world is a lot higher voltage than what computer systems use. We use 100, this is basically line current. We use that power, 115, 120, whatever the particular power is available there. We typically use this because it's available and because high currents or high voltages tend to lose less, there's less loss in them over longer distances. So I can run 115 volts across a factory or a manufacturing facility without losses in power, where if I were trying to do that with a 5 voltage line, which is what we use in the computer systems, we're liable to lose so much in the line as far as a voltage drop that it wouldn't actually be able to be detected by some of these systems. Another reason we use higher voltage is when I have contacts, mechanical contacts that are opening and closing. The high voltage and a little bit of spark that might occur tends to keep oxidation off of the contacts, where low voltages won't do that and the resistance could build up. So there's a lot of reasons why we use high voltage here, but we have to drop it down in order to get it into a computer system or a digital logic system. So that's what the signal converters do. They drop 115 volts down to typically 5 volts. Here's one way we do that inside of a signal converter. I'm showing my limit switch coming in at 115 volts, but I've got a step-down transformer. And I have a couple diodes here that rectifies it or converts it to DC. We'll learn more about that later on too. I've got some filtering circuits here. We'll learn some more about that. But in any event, I'm coming in 115 volts, and through this circuitry, now I am at a suitable voltage for digital processing. Here's a different type, 115 volts, converting to DC right away. And I'm using this DC power to pick up a relay. And the relay contacts are hooked to a 5 volt power supply of that digital logic system, and I'm taking it and I'm feeding it back into my digital system. So I've coupled through a relay. Electrically, I'm not connected. This 115 volts is not electrically coupled to the 5 volts of the system, the logic system. I'm coupled only through the separate coil and contact circuitry of a relay that's built into this converter. Now I've coming back out of my digital system, I need to boost it back up again. So I'm going to have output amplifiers for taking the 5 volts or so output of digital logic systems, PLCs, and bumping it up, amplifying it or increasing it up to 115 volts. So here I see that I had an AND gate here where this and this had to be high for this to come out, and this amplifier, output amplifier, is going to take that 5 volts and make it usable with 15 volts, what I need to drive these devices. Let's go back to this example again. The way that I had it shown before wasn't exactly how it works, but it served the purpose at the time. But in actuality, what I have here is I have my coil circuit. There's actually a relay. This is a relay. Part of this starter is this relay solenoid. So the solenoid does two things. Actually does two things. Electrically, what it does is provide contact closure for this circuit right here. So what happens here, I have some power, low current, so I can use light wire, and I'm up to my key for input 1, but I also have to have and this has to be closed, and that causes this coil to energize. And when that coil energizes, it closes a set of heavy-duty contacts that allows this high current with heavy wire to run the starter. So I said the solenoid does two things. It does. So a solenoid, we know, is an electromagnetic coil that causes a shaft or armature to move. And when it moves, it closes the contacts for this electrical circuit, but it also causes gears to be thrust out so that this motor engages with the flywheel of the combustion engine, so that as the motor turns, that gear connection causes the flywheel to actually cause the motor to turn over, the crankshaft to turn over. And once I let off of the starter, that has a spring return and it flies back in, the contacts open up so that the starter doesn't keep trying to run while after the engine started, but also it disengages that gear so that the flywheel doesn't try to run the starter off of that gear. So two functions: to close the contacts for this electrical circuit to drive the motor, and to engage and disengage the flywheel from the starter. What that would look like in a schematic would be this. I've got my 12 volt control circuit. There's my key switch, and there is my seat switch. But instead of operating the motor directly, was in our original example, I'm picking up the relay. And that relay causes these contacts to close. This is my high current circuit, and that supplies the power to the starter motor. Here's another similar example where I'm using 460 volt. These are three-phase motors. I have two three-phase motors, 50 horsepower each. And here's my control circuit. It's 115 volts. And what I do here is I've got some sort of a contact, either a switch that an operator toggles or an output from a PLC. Something causes power to be delivered to R1. And when R1 picks up, it starts this timer. Normally open, time close. So this is normally open, But the time close means that once this closes here, this starts timing, which is something that we can preset usually. And the reason that I'm doing this is because whenever I have motors start, they take a lot of inrush current. The initial starting of a motor takes a lot of current, and if I try to start too many at once, the current in the lines are so high they would trip breakers. Once these things get running, then the current drops down. We'll learn more about that too. But if I were to try to start both of these at once, the current may be so high as to just trip the breaker. So I sequence them. Motor sequencing is very common. If you've ever noticed, if you've gone through a car wash that have the blowers blow the water off, if you listen, when those start up, you're going to hear those motors start one at a time for that exact reason. You'll hear one start, and in a little bit the other one will start, and once it's going, then the other one will start, and that's to prevent that inrush current from happening all at once. So I close this. We're going to start the motors, and MSA contacts close. So I've got a 115 volt coil controlling 3 contacts that's off of that coil, and it's 463 phase power. So MSA contacts close, the overloads are okay, allowing current to happen, and that starts up. And then, since this has been timing since this closed, once it closes, now MSB picks up. The MSB coils here close, and that delivers power to this motor, and it begins. Programmable logic controllers. Here we're looking at various types of programmable logic controllers. See here, but with any of them, we're going to have some common features. Now, we talked already about logic systems having an input, an output, and in this case, the logic or the decision making is done here by the CPU. Now, this has some other peripheral devices. We've got a power supply module that supplies power to these. This is typically mounted on a rack, and these are plug-in modules. We also have a memory unit so that we program. We have a program. It's stored in the memory. We have a programming device like a keyboard or some sort of interface. We have measured signals going into the input, and we have controlled signals coming out of the output. Looking at the input module, we see that I've got 120 volts over here, and they're supplying these various switches. I've got a push button switch, I have a limit switch, this is a flow switch, different kind of switches. And whenever any of these close, that's putting the 120 volts on the input. Now, we said we have to have some sort of converter that takes this 120 volts and drops it down to 5 volts that the computer can carry. So that's what's happening in the input module. Okay, my output module here. I've got my my signal, my command coming from the PLC CPU, from the decision making or the logic. And as we said, that 5 volts that's typically used within the computer itself has to be bumped up in order to drive these high current outputs. And this output card does that. Just like with the input card, you see that we have 16 outputs. We had 16 inputs. Note the way these are numbered. You know, it says 17 right here, and it starts as 0. The reason that is, this is an octal type of numbering system, so it goes from 0 to 7, and then it goes 1 0, which is 1 8, 0 1s, 1 8, and 1 1. We'll talk more about numbering systems as we get later in the course. But whenever I get a command from an output going high in my logic, that causes the corresponding output here to supply power to my various loads. So the commands are being conducted by a speaker, a solenoid, a lamp, whatever that particular correction device or a notification device is. This is the CPU. This is showing where the logic actually resides. The programmed software, the ladder logic, all resides in here. And as far as memory and those kind of things, image files, we're not going to worry too much about that for this discussion. As you get deeper, if you get deeper into programmable logic controllers, then you will pay more attention to what's going on with these. Going back to our paint zone, our process where we're painting and diverting items, here's what that particular aspect where I'm identifying that I'm in the paint zone, that was performed with this relay logic here, as you recall. If you were to look at the same logic, the same function that we're performing here in a PLC, it would look much like this. These I's represent inputs and they look like contacts, and O's represent outputs and they are to represent the coils. So you can see the similarities between the two as far as schematics, and you can see the identical function that's being carried out in both of these different types of logic, relay logic and PLC logic. This is showing the programming device. Here I'm using software on a laptop that I interface with the PLC rack, and you can see all those components, the CPU modules, the input modules, and there's some associated hardware that's in here too. When you get into programming, you're also going to see these different schematics. You'll basically select one of these and kind of drag and drop or otherwise insert. You build your logic by using these. So one of the beauties about PLCs is, let's take our process where we're weighing and measuring and painting, diverting those boxes. If I want to make a change to that process, that's probably going to mean that I'm going to have to do some rewiring. And maybe the wires don't fit anymore, so now they're too short. I've got to cut new wire and throw the old ones away. Maybe I need more relays or relays with more contacts. If I make changes in logic that's made out of hardware components, then making changes and additions to that logic is usually expensive and time consuming. So when I have my logic that's just software based, and I can change all the connections internally, everything's still hooked up on the outside as far as my inputs and outputs. But if I want them to do different things, then I can make those changes in the software with drag, drop, delete, copy, paste, whatever, and I never have to remove a wire one from any relay or contacts. So this means examine when closed, examine when open, and different. This is based on, I think, an Allen Bradley, but different manufacturers have different designations, although they're pretty similar. You'll see some slight disparity among them. But once you get used to how PLCs work, you can easily switch from one brand to the other. The inputs that we've looked at up to now have been what they call discrete inputs. And by discrete, they mean they're separate and basically they're just on and off. So either a switch is made or it's not made, but we know that in the real world, sometimes we have situations where we're not in an on or off situation. Maybe I don't want my heat fully on or fully off. Maybe I want to vary it. And maybe the same with light. I may be measuring something in between extremes between on and off, and that's what analog input devices are for. So in this particular example, this is a variable resistor, and this is being moved probably by something that's moving. It's attached to something that's moving. So as that item moves, I get a different voltage, and the voltage that I receive at my analog input that's going into my processor is telling me where this item is, because as the item changes position, the voltage changes. And so the analog signal going into the computer is following that change. Here I have another kind of setup. It pretty much operates the same as this. It's a little more elaborate. And here's an even more elaborate version, but the same thing. But in all these cases, I'm looking at some variable, something that's changing in the real world, and translating that to a varying electrical signal, and that analog or changing signal is fed into the computer. Now, I will add this, because this is an analog signal. This also converts that analog signal into digital information that the computer can process. And analog to digital conversion is another thing that we'll talk about in a future module. In looking at control systems, we need to look at what's called closed loop versus open loop operation. What we have here is a process of maintaining level in this tank. Let's just say it's water. The desired process is to keep this desired level of water in this tank. So this is what I'm determining to be my set point. This is what I want. This is how I want this process to be. The variable is level, and this is where I want it to be, and I need to control that. In this particular case, even though I'm trying to do my process, there are disturbances in the real world that can have an effect on my process. And in this case, we'll say evaporation. Evaporation is a disturbance to this process, and because of that disturbance, this is going to change from my desired level. And it's going to drop, obviously. Now, in this particular system, how do I correct? I wanted it here, and it's here instead. How do I correct that error or that difference from where it is from where I want it to be? I have to have a control device, and this is it. So this is my output, and my input is just me looking at this and seeing, oh, it needs to be filled up some more. Now here's my correction device or my output. I'm going to open this valve and let more water in until my measuring device, my eye, tells me that, okay, I'm back where I was, and now I turn this off. This is called an open loop because this detection is not directly doing this. It's not automated. I've got to take a look, measure that with my eye, and then make my correction here. But look at this. This is what we call a closed loop system, where the variable directly affects the correction. So here's my desired level, same as before, but now I have a float. Here's my control system. It's a mechanical control system, but we still get the idea how feedback works. I've got my level. I still have disturbances that's causing this to evaporate and the level to drop, but as the level drops, so does this float. As that float drops, because this is pivoted, this is going to go down and this is going to go up. And this valve, here's my supply pipe where water's coming in. It can't get in because this valve is seated, but as this drops down, this lifts off the seat and water can go through this passage into the tank. As the tank fills, this goes up, and as it does, it closes the water off. So it's automatically adjusting for variances in the process. Here's a block diagram showing open loop versus closed loop. In an open loop, you've got your setting where you want the process to be, the process variable to be. You have your controller, you have the process, you have your disturbances, and then you've got what that actual variable is. With a closed loop setting, you set your set point and you measure that variable and you compare. You make a comparison between where you want it to be, the set point, and where it actually is. And the difference between the two is what we call the error. And that error correction is performed by the controller, which has output devices that will make changes to get this variable back to where it needs to be. Here's the feedback loop here that's a little clearer. I've got my set point and I've got my comparator, because this is circuitry. This is circuitry. I've got my set point in this case is probably coming from, let's just say, a dial. Let's just say I've got a dial on my operator station, and when I change that dial, it's moving a potentiometer that gives me a voltage that represents where I've got the dial set. And maybe I have that set at 50% light, and I've got a process which is light, and I've got a measuring device that measures the light, and this tells me how much light I have. Do I have the right amount of light to where I want it to be? So let's make this a little bit different. Let's say I'm looking at light, but that light is shining through a fluid, and the amount of light that I get is dependent upon how transparent or opaque that fluid is. So maybe I'm processing this fluid to have, maybe it's glass, whatever I'm processing, let's say that I want it to have a certain amount of transparency, and I can measure that by how much light gets through. So if I'm doing my glass and I'm measuring the light to tell me how transparent it is, and I see that I'm getting too much light, then I know I need to make the glass darker. So I've got something that measures my light. I compare it to where I want it to be, and if there's a difference, either it's too light or too dark, I make a correction. My controller is going to add dye, or however you color glass, and hopefully that'll make the correction. And then if where I set it and where it actually is the same, the correction signal will be 0, so that error signal does nothing to the controllers to change the process. Let's take a look at this one. I have a rack and pinion, so I have a motor here, and the motor is driving this rack and pinion system that's going to move this object one way or the other. And this is my setting. This is an input. I want that device to be a certain place. So I'm going to move this to wherever I want my scale. I'm going to move this on the scale to tell me where I want that piece to be. So if I move it this way, and this is like string or something, if I move it this way, then that's going to cause this pulley to go up. These are fixed. These can't move. This one can move. So if I move it this way, that causes this to go up. And it's mechanically linked or coupled. What this dotted line represents are mechanical couplings. So as this moves up, this arm on this variable resistor also moves up. And as it moves up, that causes a voltage to occur on this amplifier. It causes this motor to run a certain direction. If the voltage, so here's one side of this voltage. Here's a voltage here. If this voltage is greater than this voltage, it'll run one direction. If this voltage is lower than this voltage, it'll run the other direction. So depending on which way this moves determines which way the motor runs. If I'm pulling it this way and this is going up, that means that this voltage here is higher than this voltage. In this case, that motor's going to run this way to make that go that way. And as it does, this drops back down until those voltages are equal, and then there's no difference to be amplified to run the motor. And if I wanted to go the other way, this would drop down, the voltage would be less on this side, the motor would run the opposite way, and the correction would be indicated here until I got zero difference between the two, zero error, and the correction stops. All right, let's take a look at this. Down here, I have a power source, and I have two voltage dividers. This voltage divider is two equal resistors, which means that at this point right here is basically half of this voltage here. This voltage divider is something that's variable. If this pointer is halfway on this resistor, that means the voltage division occurring on this resistor is half and half at this point. So if this is right in the middle, the voltage here is the same as the voltage here. There's no error between these two, so there's no difference in voltage that can be amplified to run this motor. This motor is run by this power coming from this amp. So right now, if this is halfway, we'll consider that to be a balanced situation or a balanced condition with no error existing. All right, so what this is, let's just say this is like what they use to make copies of your keys, and you put your master key in here, and now I'm going to make a duplicate. And this piece moves right here, so this piece is going to start here, and as this moves this way, this will follow the contour of the key. And this is a little assembly here that's on a spring, and that represents a pivot point, so this can pivot. And as this moves, and this follows the contour of the spring, this is going to move up and down. And when it moves up and down, this is going to move up and down. And with it, it's going to pull this wiper on this variable resistor. So if this were to move, as this is going up this way, as this is going up, that's going to make this go down, and that's going to cause the wiper to move this way. If that's the case, that's going to put a smaller voltage here than what's over here, and that's going to create the error, the difference in voltage between these two. That's going to cause that error to be amplified, and it's going to drive the motor up into this so that it'll cut into that. And as this changes its position, changing this and changing the voltage, this voltage is going to rise and fall in comparison to this, and that change in voltage or error represents changes in the contour, and the correction device causes changes in the motion of that, which causes this cutting disc to follow the contour of this and replicate it. Let's take a look at this closed loop system for controlling temperature. Here I have a thermostat setting. I'll set my set point. The desired temperature will say 120 degrees. And here I have a circuit that can supply power to a gas solenoid right here. So my gas supply is in this pipe. It's being blocked on its way to the burner, and the way to open that passageway is with the solenoid valve activated here. So whenever I complete the circuit, this will open, gas will flow to the burner to be ignited. So we can close the circuit with this switch. This is a mercury switch. Since mercury is conductive, if this mercury comes in contact and comes between these 2 points, that will complete the circuit, causing that to energize. So how does this work? Right here is an important part of this process. This is a bimetal strip, and we talked about bimetal strips. They have 2 different metals, and they're fused together, but they have different coefficients of expansion. So as it's heated, it will tend to bend. So in this case, in this coil made out of this type of material, As this cools, it's going to contract, and as it heats, it'll expand. So as this expansion occurs, this will tend to rotate this direction. This is a rotatable shaft here. Um, and as it cools, it'll tend to tighten up, causing that to move this way. So I can preload or put some tension onto this spring that positions this somewhat. And then it can also be positioned as it cools, contracts, and expands. So let's say we put it at 120 degrees and the temperature is less than that. Because of that contraction causes this to move to where this will come in contact to that. It'll start to heat up. And as it heats up, this will expand and this will start to move this way until the mercury comes off of these contacts and the solenoid valve will close. That particular type of control, where I'm operating a solenoid valve, that type of controller is called an on-off control mode, sometimes called a bang-bang control because it bangs on and off at its set point. And if you look at this graph here, this shows the percent of valve opening at different temperatures. And if the set point's 120 degrees, as it is here, we see that any time that's below 120 degrees, the valve is 100% open. That's the only two positions that valve can take is 100% open or 100% closed. So below the set point, it's 100% open, supplying gas to the burner, and the temperature starts to rise. As soon as it gets to 120 degrees, the set point, bam, the valve goes to 0% open. The valve is off and the fire goes out. And looking over here, we see what's actually happening in the temperature in response to this controller action. You see that even though the valve at 120 degrees, the valve will be going off, the temperature continues to rise even without the fire burning. So why is that? Because there's residual heat in the burners and the firebox, the components that's been there, the air surrounding the burner. That residual heat still causes the process to increase up to a point, and then it starts to fall again. Once it gets down to 120, bam, the fire kicks on again. But it takes a while to heat back up. So the temperature will continue to drop to a certain point. We see here we're looking at plus and minus 5 degrees around the set point. Once it kicks on here, it'll continue to drop, but after a while the heat starts catching up and the temperature will rise. So this cycle will continue with this minor variance around the set point over time. And if you look at in minutes, as this is occurring, you see that every minute this valve is changing states, going from off to on, staying on for a minute, then going off, and it's off for a minute. So if you think about that, every 60 minutes, this thing is flipping on and off 60 times. Now that's maybe good, but you got to remember that these things have a certain lifespan, and turning things on and off, especially things that are this rapidly changing, turning them on and off with high frequency just causes them to wear out quicker. And maybe that's okay, maybe it's not, depending on what you need, because I can get tighter control than this. If I can't tolerate this much of a swing, I can get a different type of controller. So this oscillation that you see here is common to a lot of processes, and depending on the amount of variance away from the set point, sometimes that's tolerable and sometimes it's not. There's different types of controllers, and as you get tighter and tighter control, it's going to require tighter and more complicated control systems and controllers. With that complexity, troubleshooting systems when there are failure is complicated. So you want to use the easiest way that you can get the job done. You don't want to overkill because also they get more expensive the more precise they are. So maybe this type of variance in your process is acceptable. So maybe an on-off controller is like your thermostat in your house is perfectly acceptable. And if it's not, then there are other things that we can do to try to get tighter control. Here is a slower acting, this dotted line shows a slower acting valve, so that doesn't like slam open and slam shut like a lot of solenoids do. It's somewhat buffered, which reduces the wear and gives it a longer lifespan. Another way to increase the lifespan is by having it go on and off less over a period of time. And a way that you can do that is by using this differential gap. This is a feature of on-off controls. And this is something that's adjustable. And you set this differential gap is it gives you a margin on either side of your set point that this will act on instead of acting right at the set point. In this particular example, we've adjusted this particular controller to have a 6-degree Fahrenheit differential gap. That means it's plus and minus 3 degrees around its set point. So looking at valve opening, below the set point, the valve is open and it's staying open, supplying fuel. And when it gets to 120, it doesn't snap off. It goes ahead and goes that extra 3 degrees and then it shuts off. Now, as it's starting to cool, the temperature is coming down. It doesn't open up where it had closed. It doesn't open up at the set point of 120. It waits until it gets to that 3 degrees below set point and then opens up. So this extra time, this extra gap around the set point, as you see, it's toggling 50% less. Now it's taking a minute and a half instead of a minute. Reduce the amount of cycle time by 50% so that you can expect this to last longer because of that, 50% longer. Now, the consequence of that is your oscillation is greater. Now, instead of going 5 degrees over around my set point, I'm going all the way up to here. So it's a much higher oscillation, but less frequency in the operation of the controller. You have to weigh this out. What's more important to you? If you're not going to notice this in your process, if this doesn't make any difference in your final process, then now you've been able to extend the life of your parts and your equipment by doing this. If this is not tolerable, this amount of swing, then you've got to go back to the previous version or adopt a more complex controller. The proportional control is a type of controller that provides a little tighter control over those oscillations. Because it's not slamming on and off, it's proportional. The correction, the output correction that's being performed is proportional to the amount of error that exists between the process variable and the actual set point. So in this particular example, we have some sort of a product that's moving through this heat chamber with burners, and it's going to come out the other side at a certain temperature. And we're looking at that temperature. At 180 degrees, we've set this system up that if we want 180 degrees on this metal coming out of here, or whatever this is coming out, if we want it to be 180 degrees, this variable valve, a variable position valve, has to be open at 40% for 180 degrees. So the gas can be supplied here. This valve is not just on and off. It's like a butterfly valve that can open and close gradually. If we have a 5-degree error, that corresponds to a 20% opening change. Okay, so it's 5 degrees per 20% opening. And it's proportional because if it goes down another 5 degrees, we see another 20% opening. The proportionality is going to exist there between the amount of air and how much valve opening is supplied. We can adjust that percent of proportional control, the proportional band, and we look at where we want the valve to be all the way open and where we want the valve to be all the way closed. And that degree range compared to the entire range of control. So this particular controller will work between 60 degrees and 300 degrees. So that's a range of 240 degrees. We want it to work. The proportionality we want is we want to do these 48 degrees, that's between these 2 points of 100% open, 100% closed, and this is something we're setting up on purpose. That gives us 20% control. Our proportional band divided by the whole range of control gives us the proportionality band in terms of percent. And you see that we can adjust this to different rates. So the steeper the slope means a smaller change in the signal. In other words, a smaller error is creating a greater change in valve opening. So proportional bands controllers, the slope is determined by its sensitivity. Here, a very small change occurring in the air causes a big change in correction. Here, it's about 50-50. A moderate change in temperature in your air, and you get a moderate corresponding correction. So this is going to be a little slower to act. This is going to be much quicker. This is going to be tighter control than this. But look at this. The smaller this band gets, this is 100 and this is 20, the smaller this gets, the more we approximate an on-off controller. In fact, if this gets to 0, to where the slope is just straight up and down, then we have the same thing as we had in our on-off controller, and we'll get those oscillations. This reduces those oscillations greatly. Now, as I said, the tighter control that you want, the more sophisticated the controller may need to be. And with that sophistication comes complexity in the troubleshooting of the system, comes more expense in the design and construction of those components. So there are consequences that you have to weigh out. How much control do you really need? Here we have a process variable that we're measuring, and we have a set point where we want it to be. This is the comparator, and the difference between where we want it to be and where it actually is, we're calling the error. And we have, in this case, a gain, so we're going to maybe amplify that error, or maybe not. But I may have a proportional controller here, like we just looked at, and that's going to control our output, the correction devices. If this particular type, this straight through right here type of control is inadequate to give you the tolerances that you're desiring, the next step up is an integral controller. Because in a proportional controller, even though you have a set point and even though you have this process variable, it will never quite catch back up to the set point. There'll always be a little bit of an offset, and that offset occurs because you're opening a valve to a particular spot, and if there's a change, that disturbance is going to be there all the time. And essentially, if you've got it set, got the valve open at 20% to keep it at a particular temperature, and now the surrounding air gets colder, causing that temperature to drop. And now I've got to open the valve a little bit more to give me the added gas and heat. And as it starts to heat up, the air will come down, but it can never get down to the set point, because if it did, that's not enough fuel to get to the temperature that it needs to be because of the disturbances. So this type of controller has advantages, a lot of advantages over on and off because you don't have the oscillations, but it's not completely ideal. So if you need to have that offset removed, the integral controller can be added to it, proportional plus integral. The integral works in such a way, because of the circuitry, that if that error still exists after the proportionality part has done its job, now this kicks in and it provides extra gain to the controller correcting device, so it maybe will bump that valve open just a little bit in the case of the heating example that we're using. And if that's not good enough, we can kick in the derivative type of controller. So if you've heard of PID controllers, we're talking about proportional, integral, and derivative. This operates, the integral part operates off how long the error exists. So if there's a correction by the proportional and there's still an error, then I'm going to increase the gain. If after a certain amount of time it's still there, I'm going to increase a little more gain. So the longer that error is there, the more I start turning up the system until that error goes away. Here, I've got a rate of change. This is based on how long the error is there. This is based on how quickly is that error occurring. Because if we see the process variable changing rapidly, it may be heading out of control of these. This responds when it sees a fast change, it sees a high rate of change in the process variable, it kicks in to try to correct. These are already trying to correct, but if it's still happening, if that change is still happening here and it's happening quickly, now this kicks in to help. And between all three of these, this provides very tight, although it's a very complex system, very tight type of control. Input devices. Input devices are used to gather information to supply to the controller, to the processing unit. Whether it's a PLC, whether it's computer-based processing or relay, whatever's making that decision based on the inputs, this is where that information is coming from. And a potentiometer, or a variable resistor, is one way that we do that. This is good for measuring positions. And maybe we're just using this as a dial to provide a set point. I've got a dial where I want my set point to be of a process. I may use a resistor like this to turn that dial. Or here's a slider. This is linear, where this is rotary. If we talked about variable resistors before, we can see that if I have a voltage from here to here, this acts like a voltage divider, and the voltage between here and here will increase as this goes this direction. In this case, the same similar thing, I have a voltage divider, so whatever my voltage is from here to here, this will tap off of that. If it's in the middle, then half of this total voltage is here to here. If this is down to 25% of this resistor, then 25% of the voltage is here. And let's say that this is connected to a cylinder, and as that cylinder moves, it also moves this slide. So I can relate the position of that cylinder to the voltage that's coming back to my controller from this particular resistor. Here I'm looking essentially at the same thing. My V out that goes to my controller is the result of voltage division of this DC or AC voltage source being divided among the length of this resistor. In this case, what I'm looking at is a balanced, and I'm comparing a plus or minus situation. This is going from, say, 0 to whatever the max voltage is. So I'm looking at a 0 to some positive number. But here I can reference above or below a point. So I can actually convert this into a positive negative if I want to use this point as 0, because I've got this voltage divided in half by these two resistors. And I'm comparing that voltage, half of this voltage here, I'm comparing that voltage to whatever voltage I'm tapping into here. So if this were at 50%, then the difference between this voltage and this voltage would be 0. However, if I were to slide this down, or if it were attached to a cylinder or anything else that was moving this half down this way, then we would see that this voltage over here is going to be smaller than this voltage, which is going to give me an error in one direction, which will drive my controller in one direction. And if something moves this up here, then this voltage is going to be higher than this one. It'll be positive in relationship to this, and my error will be the opposite polarity, and the correction will occur in the opposite direction. Another similar situation. This device is an LVDT. This is also a way to measure position or movement. LVDT is a linear variable displacement transformer. And the way it works, here's what it would kind of look like. The way it works is like this. I have a primary winding. It's a transformer. So I have a primary winding, and I have two secondaries, or a secondary that's kind of split in half. So I've got magnetic flux that's being created in the primary, and both of these are subject to the flux inducing a voltage in them. Now the core is what's actually hooked to my device that I'm trying to measure its motion or its position. So as something is moving, then this is going to move because it's connected to it. Now as it moves, it's going to allow more or less flux from the primary to have an effect on these secondary coils. In other words, if this device moves down, then the voltage that's induced in this winding is going to be much greater, because there's going to be a much greater transfer of flux because of this core being in there, than up here, because now this will have moved out of the way. This voltage will be much lower. On the other hand, if this were to move up, the opposite would be true, and this would be higher than this one. So if you look at that, you see that you can have a positive and negative voltage that's coming out of this movement of a piece or device. These are Borden tubes, and they essentially work the way that these party favors do. If you have pressure in this thing, it tends to curl outward in all these cases. Pressure. So that's what this is used for, to measure pressure. So we were looking at the previous two cases with the LVDT and the variable resistor. We were looking at position or movement. This is the device that helps us measure pressure, because this responds to the physical phenomenon of pressure. If we attach that now to a variable resistor, like we've done here, then we can, or an LVDT as we've done here. So now as I increase the pressure in this, that translates to motion, which I can feed out to my logic. So increased pressure, it causes an increased signal. I'm translating physical phenomena to an electrical output or electrical signal. That's what transducers do, convert physical phenomenon to electrical signals. Here's another type of pressure transducer, bellows. The concept is pretty self-explanatory. If I have a bellows and I increase the pressure, it's going to expand, move, and if it's attached to an LVDT in this case, or a variable resistor here, again, I'm translating pressure into movement into electrical signal through this type of device. So the transducer here, I would see this thing that looks like this. These are examples of transducers. In this case, it's not a switch, it's a pressure transducer. A pressure switch would just open and close at a predetermined and programmable, settable set point. But these are going to give me a varying analog signal based on changes in pressure. So it would look something like this. Here's my leads that would be going out, electrical leads going out to my controller, and this would be the part that would be exposed to the pressure. And as the pressure increases, the signal coming out of here also increases in an analog fashion. If I want to monitor and measure temperature, a thermocouple is a good way to do that. Here I have two different types of metal, and as we talk about coefficients of elements, we talk about expansion, but also there's resistivity and conduction, and in this case we're looking at how much difference does heat cause electrons to move in these two different materials. If I have these two different A and B metals and they're twisted together and I expose this to high temperature, then one of these metals is going to move more electrons because of that heat than the other. That creates a difference in charge. That's a voltage. And that voltage we can use, like right here, to represent changes in temperature. As the temperature rises, the difference is going to increase. We can measure that increase as a voltage, but we know that what we're really looking at indirectly is the temperature. Here is the device that basically it's a resistor that its resistance changes. Remember we said if we have a symbol with an arrow through it, it's variable. In this particular case, it's being affected by temperature. The resistance changes as the temperature changes. So this might be the type of temperature sensor you might find in your automobile, in your cooling system, or in your fuel delivery system. As the temperature rises, the resistance changes so that I can measure the current that's going through that resistor. And as the resistance goes up, because the temperature is going up, the current's going to go down. I can translate that, or the voltage that develops because of the changing resistance, into a temperature change. Here I'm measuring light, and I'm going to use PV cells to measure light. In this particular case, you see light waves coming in. It's a variable voltage source. The difference in light causes a difference in voltage. That's how PV cells work. Some elements are so sensitive to light that photons striking them will cause the electrons to dislodge and move. So silicon's a good example of that. Struck with photons, light, electrons move and then move from one place to another. That gives me a difference in charge and a voltage. So I can use these devices, light, to maybe measure, like we talked previously, how opaque a material is, a fluid or a glass or a plastic. I can measure air quality by how many particles in. I can use them also just as on-off switches so that when something comes in front of this, block the light, and my photocell will lose its voltage, and that'll indicate something's there. In a case like that, I don't have to use limit switches because sometimes I can't actually touch the object that's being moved. Maybe it's too hot to be touched. Maybe it's too far away that if we had a limit switch arm that long, it would be wobbly. There's a lot of reasons why we might not be able to use a physical limit switch, but we can accomplish the same thing by detecting presence of something with a setup like this. I have a light source and I have a lens that focuses that. It's aimed at a PV cell. So if something comes between here and blocks this light, obviously this voltage is going to change. In this case, the way this particular circuit's set up is like this. I have my light source and the focusing to focus the beam. and it's striking directly on this photocell, causing a voltage to cause current to flow in this relay, which picks up a set of contacts that goes to my logic. So as long as there is nothing blocking this light, this relay's picked up, and I'm sending power to my logic saying that we're clear. If something gets in the way here, this voltage goes to zero, this drops out. My control logic knows that. It knows that there's presence of something in between that and will act accordingly. The same type of situation, but in this particular case, I'm using a transistor for amplification. We'll learn more about that in a future learning module too, and about getting the same results. Here, this particular device has the light and the sensor in the same unit. So in this particular case, I've got my light source and a one-way mirror that coming out this way, the light will pass through out the beam focuser, and it hits a mirror or some sort of reflective surface, bounces back, enters, and coming this way, it's reflected onto my photocell. And my circuitry that we saw up here is included in this. So I've got a couple wires, terminals on this. I've got three. If you look at the bottom of this, there's going to be 3 screws, one for power going in and 2 for coming out, one on a normally closed set and one on a normally open set. If something gets in the way here and the light doesn't get reflected back into here, obviously this voltage goes to 0, as in these examples up here. Here we're actually using a photocell for measuring a liquid's translucence. Another type of input device is an encoder. This particular type of encoder is an optical encoder. These devices are used to measure rotation. If I have this attached to a object that's rotating, like a pulley, like a fabrication roll, like it would be in a paper mill or a steel mill, anything that it's rotating, and I want to know how far it's rotating in degrees. Maybe it's not going all the way around over and over. Maybe it's not rotating like a fan, but maybe it's just rotating maybe half of the way this way, maybe a fourth of the way this way, but I want to know where it is. This provides that input. This lets me know where my process is. If I want to rotate a piece 40 degrees and I move my indicator to move it 40 degrees, how do I know when it's got there? I'll use this device to tell me where that process is. And the way that it works is inside I have this wheel, and there's these slots all the way around it. Now there's not very many here, but in a typical encoder you could have maybe 600 of these. And note that the more of these that you have, the more you can zero in on how many degrees. So maybe there's 5 degrees between here and here, 5 degrees between here and here. So my limitation on accuracy or precision is limited to 5 degrees. If I had 600 of these, now I'm measuring fraction of degrees, so it's very precise. So the way this is set up to work is I've got a photocell and I have a light source. And here is this disc, and it's attached to something. The shaft we're trying to measure, this is attached to what I'm trying to measure. As it rotates, it's engaged with a gear to rotate the shaft of this encoder. And as this shaft is turning, then my photocell is picking up light from the light source every time a slit passes between the light source and the photocell. That produces a voltage just for the time that hole is present, and then when it goes dark again, the voltage goes away. So you can see these pulses that are coming out, and if I know how many degrees are between each slot, then I know how many degrees are in between each pulse. And so if I count the number of pulses, I know how many degrees this has turned. And if I set this up to measure, I want it to move in this, oh, it says right here, this particular one's 15 degrees apart. So that's not very precise. But so I know that there's 15 degrees between this pulse and this pulse, this pulse and this pulse. So if I counted 3 pulses, I know that it has moved 45 degrees. Another application of this is using it as a tachometer, because if I know how many degrees I'm rotating against time, in other words, how fast are these coming, if I can get 360 degrees in 1 minute, then I have 1 complete revolution per minute. That's 1 RPM. So if I'm measuring these, counting these to get my degrees, and then timing them, now I have RPMs, rotational speed. Here's another case where I'm not directly touching the process for whatever reason. I've seen these be used in tanks filled with fluid where I don't want to put a float switch down in it. Maybe it's dangerous if it's a very flammable or explosive substance in the tank. I don't want to have electrical connection down inside the tank like would be on a float switch. Maybe it's very corrosive that it would just eat a float switch up. So what we've done with this is we place a device like this at the top of the tank, and it never touches the material that's in the tank, and it might look something like this. Any of these are good examples of what they would look like. And the way that it works is it shoots out ultrasonic waves and then measures what's reflected back. So the longer that it takes for this wave to bounce back, because it shoots it out in little bursts. So it'll shoot out a burst and wait to see how long it takes. It starts the clock as soon as it shoots it out, and it waits to see how long it takes for it to come back. The time that it takes is a function of the distance between the sensor and the material that it's looking at. This is an inductive pickup. The example that I've used is a crankshaft positioner on a car, but here's an example where I'm looking to measure rotational speed or position. In this case, I'm actually trying to find the position of the crankcase. And how do I know? I've got this pin right here that when it comes by this inductive pickup, it'll cause a signal. How does it work? Well, here's my rotor that's got my pins on it, and here is a coil of wire around a magnet. And we know that if I can move the lines of flux across these conductors, that will induce a voltage. So if this were completely stationary, these lines of flux from this magnet are not moving, so there's no cutting of flux across the conductors, and there's no induced voltage. But as this piece of metal comes close to this, those lines of flux are drawn toward it, and as those lines of flux move, they're going to cut this conductor and induce a voltage that we can measure. And we'll get an output from this particular device like this. As this approaches, the lines of flux cut and cause the voltage to be induced up. Output devices. Output devices are used to make the corrections to our process. And this example that we have right here is what a typical solenoid valve looks like. You see the inlet port here, the outlet ports on the other side. Your wiring for your solenoid, your coil, is up here. And if you look at a cross-section diagram of this, you'll see that here is my inlet. The gas will come in here, and it can't go this way. It's blocked, and it can't go anywhere else. So right now the gas enters to this chamber and is restricted for any further movement, unless this valve seat lifts off of here, in which case this becomes open, the gas can travel through this passage and then out the other side. So here is the valve, and we're going to operate it because it's steel. We call this shaft and the pin the armature of this. We're going to move this with an electromagnetic field. We've got this spring that's pushing it closed, but if we create a magnetic field in this coil, that magnet will cause this thing to move up and gas will flow, or whatever, or fluid. Then once the coil is de-energized, the spring will shove it closed again. Sometimes valves are too large to be opened with a solenoid. And here's a case where we've used a motor-driven valve. Usually the motor and a gearbox is used to open a valve. And I'll show you a picture of one on the next slide. But just note that there are cams on this motor, mechanically attached to the shaft is what this dotted line means, a mechanical connection, are cams that are on that shaft. This particular one has one cam lobe, and this one has two cam lobes. And the on-off controller that's used here uses A to open the valve and B to close the valve. And the power to turn the motor comes from here and has to get from here to here. So what possible paths are there? I come this way. Here, this cam limit switch has this open, so there's no path of current here. If I come in here and it's neither calling for close or open, we can't go anywhere. If it's calling for close right now, I can't get power to it. So right now, this is in the closed position because there's no way that we can tell it to go closed. So stay with me here. Let's assume it's in the closed condition and that this motor turns clockwise. Since it's in the closed position, the only thing that I can do is tell it to go open. So the controller gets the input and decides that it needs to close A to make a correction. A closes, power comes along this line, and it goes through this limit switch contact. Can't go that way because that's blocked, but it can go this way, and the motor starts to turn. The motor starts to turn clockwise because now it's getting power through this direction. But as soon as this starts to turn, this cam comes off the limit switch, and the limit switch falls down on this set of contacts. Well, we're not telling it to close, we're telling it to open. So there's nothing here. This is a dead end. So does the motor stop as soon as this comes off? Because that's breaking the supply. No, because also as soon as this one comes off, this one comes off. And when this one comes off, now this falls down and makes a connection, and that power comes this way. So this kind of serves as a latch or seal-in, and the motor continues to run until this one comes around and opens this back up again. So we're looking at a 100-degree rotation. After 100 degrees, this opens up again and stops. Well, that's where the valve's fully open at 180 degrees. You see here, we see where the switches are being actuated by the cam lobes. LS1 happens at 0 and 360, 0 and 360, and limit switch 2 is operated at 0, 180, and 360. 0, 180, and 360. And we see that the valve is closed when it's at 0, it's open at 180, and then another 180, it's closed again. So every half rotation, this will go from closed to open. All right, so this ran around until it went around 180 degrees. Now the valve is open. That's what A was telling it to do. The controller was telling it to open. Now it's open. And the process continues, whatever that process is. But at some point, now that it's been open, it's time to shut it off. The process inputs are telling the controller that we need to close the valve. So as soon as we told it to open, this fell down here and supplied a pathway, but B was open, so nothing happened. But now we're closing B, and I have the power coming in, going through B, and since now this is down here, I'm having the motor turn. Again, the same direction, clockwise, and this falls off as before. As soon as it starts to rotate, that falls off and it seals in the power. So this continues to rotate for another 360 degrees until it ends up over here. So the opening and closing is accomplished by 180-degree rotation, which is accomplished through these cams positioned as shown. So here's an example of what that motor-driven valve might look like. You see the valve here. This is the port. You would have the input on this side, the outlets on this side. This butterfly valve is what regulates the flow between the input and the outlet. What it might look like inside a pipe, you can see here. I've got they're calling it a damper. They're calling this valve, butterfly valve, a damper. And my motor driven components here. This, instead of rotating around 360 degrees, this one opens and closes just every 90. So when this is up, straight up and down, the valve is closed, as is shown here. But if this were to open 90 degrees, then that's going to allow the maximum flow. So in that particular case, we have a reversible motor, and we accomplish reversing by whether or not we're supplying power to this winding first or this winding first. We'll talk about split shift capacitors and split phase motors later when we talk more about motors, but we can reverse a motor by how we apply the power to the windings for direction. And in this particular case, not only am I driving the motor back and forth, because this is a proportional control, not on off. So I can actually vary. I don't have to go from 0 to 100%. I can vary anywhere in between these. This is telling me where I am. This is telling me where that valve is. So if I have an error of 5 degrees and that corresponds to a 20% opening, then this will move, and I'll know when I'm at 20% because the error will reduce. This is an example of a pneumatic valve, and you can see the size of this. This is much too large to be moved by a solenoid. Oh, you could make a solenoid valve large enough, but this is a much more cost-effective way to do that. And this is also proportional, a proportional valve. Let's take a look at how this works. Here's the diaphragm of this valve. It's located up in here, and this is the actual passageway. So this stem that we're seeing right here is this piece right here. So here's my inlet, here's my outlet. The valve's situated here. This pulls it up or lowers it down. And it's variable. It's not a snap action on-off controller. It's proportional. And you see that there's a spring that can push the diaphragm up, and air pressure coming in here will push it down. And that air originates with a high pressure supply. I've got a restriction here that causes this to become pressurized and regulates the flow a little bit, and it's blowing out this nozzle. Some of it can go this way and push this down. We vary how much goes this way, and by doing that, how much this goes down, by moving this piece here. You can see that as this piece moves closer to the nozzle, that's going to allow less air to escape through here, forcing more of the air to go this direction than pushing down on this diaphragm. And we control the position of this. It's pivoted right here, so it pivots up and down. We control that with these electromagnets. Here's a permanent magnet. Here are electromagnets, and as we change the current going into the electric magnet, we're going to change the interference of these electromagnets with the permanent magnet. So we can be attracted to this permanent magnet or we can be repelled, and how much depends on the strength of the current. So as there's changes in this current, which is our signal, this is our correction signal coming from our controller. If it needs a little change, we'll just get a little bit of current and consequently a little bit of movement in this, which is going to cause a little bit of a change in the air flow that's going this way, which is going to cause a little change in how much this moves. But if the signal is strong, then the attraction or repulsion of these magnets are going to cause a greater shift in this one way or the other, causing a greater change in the amount of air going here and consequently a greater change in how much this diaphragm is pushed down, moving the valve and ultimately changing the amount of flow between the inlet and the outlet. Here's a little bit of a mechanical feedback device that as this moves down. So let's say that we need this to open up more, and that means that this gets moved up this way, causing more air to go this way, pushing this down more. It says the valve opens as the valve pushes down in this particular case. So as this pushes down, it's opening the valve. And as it's opening, the feedback is mechanical, and this goes down, and it tends to pull this back to compensate for the electrical signal until that air goes away, and then this is going to start dwindling off too. Here I have edge guide device. I've got this gearbox and motor, and it's turning a roll. In this case, the material's being fed onto this roll. This is rewinding this product, whether this is paper, aluminum, steel, whatever this happens to be. It rotates and is being wound up. And I have a system here that looks at the edge, and if the edge goes this way, I don't want it to. I need to move this so that the edge lines up along the outside edge of this coil. In other words, I want the wrap to be uniform and smooth across the edges. So the way this is set up is I have a photoelectric cell here and a light source underneath the strip. And I calibrate this thing so that when the strip is halfway blocking this detector, I get 0 volts. It's a plus and minus power supply. So I'm going to calibrate this, set this up, that when the edge is halfway blocking the detector, it's at 0 volts. That means if the edge were to move one way, because the wrap's waving in the process somehow, if the wrap moves one way, I'm going to get more light. It's going to cause the voltage to go up to a positive value. If the edge moves this way and I'm blocking more light, this voltage is going to change the other way to a negative value. Or I could have it set from 0, say 0 to 12, and then I would know that 6 volts is right on the edge, and anything less than 6 volts it means it moved this way, and anything more than 6 volts it moved this way. However way you set it up, a change in this position causes a corresponding change in the light in direction, both direction and magnitude. So this information, this is my input to this process, and it goes in for amplification. And the output of this is my controller. The output of this controller is coming in right here, these electrical signals. And as before, with the situation we had before, I've got a permanent magnet and I have electromagnets, and the strength of this electromagnet in Proximity of this permanent magnet causes movement either one way or the other, depending on the direction that this current's flowing and the magnitude, how much current's flowing. But in this case, instead of opening a valve, I have this jet pipe that pushes hydraulic oil either this direction, down this port, or if it's turned this way, it directs that flow this way. So I've got hydraulic fluid that's being pumped down here, and this can pivot, and it's being pivoted by the strength of the signal coming out of this. And I'm either going to direct that fluid into this port, that's going to cause a cylinder to move this way, or it's going to pivot in this way and direct the fluid on this side of the cylinder and move the piston this direction. I have a similar type of feedback spring here, but in moving this cylinder one way or the other, so this is a bidirectional cylinder, this hydraulic cylinder is moving either this way or this way based on which one of these ports is getting the directed flow, which is based on the pivoting of these electromagnets caused by the signal. Here's that cylinder. That cylinder is going to move this roll, the motor, the gearbox, everything that's attached to this roll, it's going to move it one way or the other. So if this strip is starting to move this way, to shift this way, if this remains stationary, then these wouldn't line up. So this is going to move in such a way to line up and correct this error. It's going to shift to move the strip this way to where this comes balanced again. Once it becomes balanced, the error goes to 0, and with a 0 value, this is going to distribute equally to each port, and it's going to be a balanced cylinder. The cylinder will not move. This is an illustration showing that input part of the process. Here's the edge of that strip. Here's the light source. Here's the photocell. And we see here that the beam is obstructed for 50% of the total width of the beam. And that's going to correspond in the detector and the controller as either 0 reference point or a halfway reference point. This is showing another aspect of the process we've been looking at. Here is the light source, here is a photocell. In this particular case, I have some solid-state circuitry that's going to amplify my signal coming from the photocell, because photocells don't necessarily put out a lot of voltage, but I've got an external power supply that I can control with this. So this is essentially turning on this power transistor so that I can supply large amounts of current to my actual coil here, my actuator coil that is going to move that jet pipe, as we see here. Right here's the jet pipe that we saw in the previous example. As I change this coil current, I change the direction and magnitude of this movement, diverting the flow to one side of the cylinder or the other, thereby moving what I'm wanting to move right here. A servo motor or servo system moves typically to a certain point and stop. So in this case, the motor's not necessarily rotating, and often it's not rotating around like you would see a typical motor do for rotational motion. This is for part rotation. And we talked about encoders, where I may want to rotate something a certain amount. Or even if I have a rack and pinion situation and I want to move in a linear direction, say from here to here, whatever that device might be, if I know the gearing, I know how many or how much of a rotation needs to occur to get that amount of linear motion. So I've got a set point, and that creates an error if it's different from the actual position. So here's my setting, my set point. Here's feedback from a variable resistor that's moving with the device. In this case, my feedback's coming directly from the motor. As I move, we'll say from 0 degrees all the way here to 360 degrees all the way here. All those degrees in between one rotation are corresponding to a voltage coming with this voltage divider. So if I want it to move, we'll say 180 degrees, I would set this set point about where it's situated here. And if this is different than this, then the motor's going to run because of the difference, the error. It'll be amplified because this error is not going to be enough to drive this motor, so we amplify it. That runs the motor. As the motor runs, this will come up to 50%. Now this is the same as this. There's no error. There's nothing to drive the motor. If I want this piece to move, again, this is mechanically coupled, right? So if I want this piece to move someplace else, I'll move the set point here. Now, if I've moved this down here, it's not balanced anymore. That error causes the motor to rotate. And as the motor rotates, this will move until it gets equal to this, and then it'll stop. That means that this was moved to where I want it to be. In this process, I'm controlling the speed of a motor to control temperature. I've got my input device here. It's a thermistor probe. This is a device that its resistance changes with changes in temperature. It's shown in the electronic circuitry as here. Without having to understand completely how a transistor circuit like this operates, we can just say that the way this is drawn with an arrow going down, that means an increase in temperature causes the resistance to go down. So there's an inverse correlation here, an inverse coefficient. But we can just say that as this changes, so does the output of this circuit. And in this case, I'm changing the speed of a motor. This motor speed is changing directly as a consequence, and this associated circuitry with the resistance, with the temperature of this oil. So the way this works is I've got a hot piece of metal, and it goes into this to cool down. And it gets on this conveyor, and it rides this conveyor, and while it's in there, there's that heat exchange causing this piece to cool, and then it'll come out the other side. So the pieces go in hot, the heat's transferred to the oil, and goes out again. Now, obviously, as this happens, this oil is going to get hotter and hotter, so that the piece goes in and stays in here for a certain amount of time. It's not going to be as cooled because the previous piece has heated up this oil. So the way that I fix that is that I circulate this oil through basically a radiator. They call it a heat exchanger. That's what a radiator is. I've got a radiator, or in this case it's water cooled heat exchanger, coils where water's going around. The pipe runs through this, and the heat from the pipe is absorbed by the cool. So the water's getting heated, but it's continuously circulating. So the longer the time that the oil is in the heat exchanger, the cooler it's going to be. So the speed of the pump determines how long this oil remains in the heat exchanger, determining how cool it is when it comes out. This is always monitoring it, and it's always regulating the speed of the flow by regulating the speed of the pump. It's a closed loop system. And yeah, it's somewhat complicated, but not as nearly as complicated as some others. But understand too that this is only one part of the whole process of whatever's this piece is going through. It had to be machined, it maybe had to be trimmed, it maybe had to be pressed. Something definitely heated it up. It has to be processed even further once it comes out of here. So a lot of big systems in manufacturing facilities is really a series of sequential processes, and this is just one part of it and the associated control system for it. An op amp, or operational amplifier, is used in a lot of circuitry. You'll probably learn more about them. They're very high gain. In other words, a very, very little change in input, a very small error causes a considerable change in the output. And if I have a set point here and I'm comparing to it my actual measurement, it just takes a small variance to produce a large result. And I can weight the effects by balancing these resistors here. One of the best features of the op amp is that it's very, very easily incorporated into circuits, and you have a wide variety of design options with very little designing required. They're very easy to use and get to perform exactly how you want them to perform. And like I say, you'll encounter them more. The schematic symbol is shown here. Whenever you see this, you know that this is an amplifier, that what's coming out is considerably larger than what's going in.